The next segment of your video is going to deal with essentially doing these problems the other direction. Instead of giving you a chemical formula, I'm going to give you the percents. And from those percents, you need to figure out the empirical formula and sometimes the molecular formula if enough data is given to you. So number one, to do this, you need to know what an empirical formula is. Okay? And all an empirical formula is the lowest whole number ratio of the atoms within a compound. Okay? That's what an empirical formula is by definition. A molecular formula, the formulas we've been making for molecules, are not the lowest ratio. Remember, we didn't reduce those. They are the true representation of how the elements have come together. So if you look at this, really, ionic compounds are always empirical formulas because those are the lowest whole number ratios of the elements. Molecules, on the other hand, aren't empirical formulas. But with this particular problem set, we can only get empirical formulas out. So to get the true formula, you actually need a little bit more information, and I'll show you how that works. But for an example here, looking at that benzene molecule, C6H6, the empirical formula, the lowest whole number ratio, is just CH, and that's all the data that we could get out of this type of problem would be. If we needed to know that it was C6H6, we would need a little bit more data to deal with that. Okay, so we're going to do problems the other direction. We're going to get from percent to chemical formulas, and the chemical formulas that we produce using that method will always be empirical formulas. So they'll always be the lowest whole number ratio of the elements within the compound. How do we do it? Well, it's very similar to the problems we were just doing. Okay, we'll be given percents, right? And those percents really can be, in the end, looked at as though they were masses. Okay. In that, if we said, okay, I have 75% of this particular element within my compound. Well, if I had 100 grams of this sample, then 75% would be 75 grams. Okay? If I have 20% of this element in the sample, if I had 100 grams, that would be 20 grams would be 20%. So choosing to say I have a 100 gram sample and therefore my percent equals grams is just an easy way to do these problems. The truth is you could decide you had any sample size. Okay, I have a 25 gram sample size. Well, then you would just have to go through and figure out, if I had 75% of this particular element in my 25 gram sample, how many grams is 75% of 25? Okay. So saying I have 100 grams is just an easy way to do these problems. So here's how we're going to do the problems. We're going to list out all the elements in the compounds. Next to them, I'm going to write down what their percents are, and I'm just going to change them to grams right away because it saves me a step. And now here's the trick, and that's why we learn this type of problem right now. I'm going to convert all of my grams to moles. Why am I going to do that? Well, because the data that's given to me is in mass. In the end, I want a chemical formula, and my chemical formula is not telling me relative proportion based on mass. Those subscripts that we generate were all based on counting, right? You'd have like 1 carbon to 2 oxygens in carbon dioxide. Now, by mass, the proportions will be very different between carbon and oxygens because the carbon atom and the oxygen atom mass differently. So to be able to use mass data to get a chemical formula from it, you make mass into mole. By doing that, we now have a count of each element within our compound rather than a mass of each element in our compound. Okay. Once we have a count of the number of moles we have of each element in a 100 gram sample, all we do is look at that count and we look at a ratio of that count. In 100 gram samples, if 2 of the elements have 3 moles and one of the elements is just 1 mole, then now you have a proportion of counting of 1 to 3, and you can generate subscripts from that data. Okay. So this problem type is the more complicated of the 2 problem types by far, and there's a lot of I'm not 100% sure of why she's saying to do it this way, but it works, and in class I'll do it again for you guys so you see it. But we're going to do an example problem right now. Okay. So this is the example problem. I'm given percent data for barium, sulfur, and oxygen within my chemical compound. Okay. And from that, I want a chemical formula. So let's do it. So the first two steps, write down all of your elements within your compounds and write down your percents as grams. The next step was to take all these grams and make them into mole, because right now we can't compare count based on mass, because one of those things weighs more than the other two. Okay? So you have to get them to count to get a chemical formula, and the count we use in chemistry is the mole. Yes, 6.02 times 10 to the 23rd particle, but it doesn't matter in the end, because 1 mole will be the same as 1 mole regardless of the identity of the element. So to get barium to mole, multiply, draw my line, gram per mole. I have a relationship between gram and mole, and it's called the molar mass. So the molar mass of barium, if you read the periodic table, is 137.33. 1 mole gram. Molar mass of sulfur, if you read the periodic table, is 32.06 gram per mole. For every 1 mole of oxygen, based on the periodic table, oxygen weighs 15.999. Now, you'll notice here these are just straight up their molar masses. It's not like times 2 or times 3, because I don't know the relative proportions. So all I'm trying to figure out right now is the count. How many moles of barium do I have if each mole is going to weigh 137.33? And how many moles of sulfur do I have if each mole is 32.06? So if you do this, you get numbers. So that gets me a count, a relational count for each of these elements. Okay. Once I have a count, I said you divide your lowest number. You take all of your big numbers and divide them by your lowest number. And that's just going to get me a relative proportion so that I know what my ratio is. So if I look at this, my lowest number is 0.4282. And if I divide this number by this number, I get about 1. And if I divide this number by this number in my calculator, I got an answer that was pretty close to 4. So what that says to me is this is a 1 to 1 to 4 ratio. Those become my subscripts. Okay. So then I have 1 barium to 1 sulfur to 4 oxygens. And you can see you generated a chemical formula that makes sense. Okay, you have barium sulfate. Barium is charged of +2, sulfate is charged of -2. Those actually balance out. And you got all that data from percent composition. This is what's done in lab a lot to analyze what a compound could be. I think we'll leave it there for this video. Okay. Go on ahead and do the form and have a great night.